Okay, great. Yeah, so this talk is about, as you can see, and as Marcus just said, connexive relevant logics. This is a somewhat new project that I've been working on, and so I'm going to present some preliminary sorts of results and gesture in the direction of questions and issues that I think are interesting and should be addressed. I should say for questions during the talk, if you do have a clarificatory question, I'm happy to field it mid-talk, but I should say that when I have my slides open so I can see them, I can't see you, so you'll have to interrupt me verbally if you want to ask one of those. Great, okay, so negated implications in connexive relevant logics. I'm going to start by telling you a little bit about what relevant logics are, what connexive relevant logics are, and what connexive relevant logics are, at least how I'm using that third term, what they are and why you might care about them. Then I'll settle some notation and fix some definitions to be going on with. And what I'm going to be talking about today are a pair of issues that often come up when you try to combine connexive principles with at least the standard, let's say, Anderson-Belknap style relevant logics. In particular, the issues I'll be talking about have to do with triviality. Some of these logics do trivialize. And another problem related to negated implication formulas, which I'll refer to as unsavoriness. As you'll see, the problem basically amounts to the fact that in, let's say, most connexive relevant logic, so long as you've got enough vocabulary around and you've got enough principles around, you can prove every negated implication formula, which is at least unsavory, if not outright trivializing. I'm going to talk about how this unsavoriness arises, and the bulk of the talk is going to be concerned with avenues for avoiding this result, and basically looking at the prospects of how we can construct connexive relevant logics to avoid it. I'll talk about 3 avenues, which I'll go into as I get there, and then tell you a bit about what work is still to be done in constructing some of these systems and proving some core results about them. Right, so anyone who's seen me talk in this August Colloquium series or in any other venue has heard some form of this, so I'll try to be quick. Relevant logics are a species of non-classical logics aimed at providing, in my opinion, an alternate formal account of the concept of logical consequence, which gives due pride of place to the notion of relevance, which places a constraint according to which for a premise A or some collection of premises to entail a conclusion B, the former must be relevant to the latter. And the most well-known formal fleshing out of this relation of being relevant to is captured in Newell-Belknap's variable sharing criterion, according to which A entails B, just in case A and B have an atomic subformula in common. And the rough idea of this is that the atomic formulas are the bearers of topic, or if you like, meaning contents or something like that. And the logical connectives allow us to arrange these contents in various ways so that when A entails B, it should be, or it must be, that the formulas A and B should have some, again, topic or meaning content or something like that in common. Note, this is meant to apply to propositional logics, and that's all I'm going to be talking about. I'm not going to talk about quantifiers at all here. Relevant logics are usually presented as formula systems using Humberstone's terminology. That is, given a language, FM, a logic is going to be a collection of formulas in FM, which will satisfy some other properties that I'll define in a moment. And then in that setting, entailment as a notion is expressed by a connective, written with this arrow symbol here, so that we get, if we take var A to be the set of atomic formulas of A, that a logic else satisfies the variable sharing criterion, just in case whenever A arrow B is a theorem of L, then A and B have a common atomic subformula. Other criteria have been proposed as being related to relevance. One that I'll mention very briefly is the Ackermann property, according to which if you've got a nested implication of this form, the leftmost antecedent of it should have at least one occurrence of the arrow. This latter holds for some weaker relevant logics. I'll say a bit more about one of them or a couple of them, and has been defended as allowing us to avoid certain modal fallacies, but can be seen more generally as requiring that entailment claims are only entailed by further entailment claims. Here is an axiomatic presentation of the relevant logic B. As you can see, the axioms here essentially tell you that B has distributive lattice logic, or builds on top of distributive lattice logic with a negation, something often called a De Morgan lattice negation or a De Morgan negation, which satisfies all the De Morgan laws of double negation equivalence. And in addition, we have some other rules like a modus ponens rule, an adjunction rule, and a pair of rules which are often called by the names of prefixing for this one on the left, RB, and suffixing for this one on the right, RB prime. And I should note, just to start, the way I'm going to define a derivation and a theorem, these are, again, in Humberstone's terminology, rules of proof. So they allow you to go from theorems of the system to further theorems of the system, but are not rules of inference in, for instance, the sense in which modus ponens is in, say, intuitionistic or classical logic. So here's B, and I'll note that in the presence of these two fixing rules, prefixing and suffixing, we can derive right away a hypothetical syllogism rule, which I'll call RHS. So a derivation, this is more or less standard, is going to be a tree, each node of which is labeled by a formula, such that each leaf of the tree is an instance of an axiom. Each interior node is obtained by applying one of the rules to its upper nodes or to the formula labeling the upper nodes. And when A is the root of such a tree, it's a theorem, and I'll write that like this, as I've already done at least once. When the proof trees don't fit on the slides, I'll cheat and write them as linear sequences of formulas, but it amounts to the same thing. We can obtain some well-known extensions of B by adding some of these axioms, an axiom form of contraposition. Note in B, we only have the rule form, allowing you to go from theorems to theorems, whereas having the axiom form allows us to make these sort of contraposition moves in the context of more complex formulas. In addition, we've got axiom forms of these two fixing principles. There's a contraction axiom, and this thing which amounts to a version of the law of excluded middle, and a pair of rules that have to do with permuting antecedents. This are a rule and an axiom having to do with permuting antecedents. The final rule C is just the full version of permutation, allowing you to permute the order of nested antecedents. And this rule form allows you to do it in a very specific context. If we add all of the above except the last one, we get the logic E for entailment. And if we add C to that, that gives rise to R, the logic of relevant implication. I'll talk about those two, and I'll talk a bit about B. And I might mention here or there some other systems we get by mixing and matching some of these axioms and rules. But in any case, this is basically the playground I'll be in with respect to relevant logics. All of these satisfy the variable sharing property. At least R does, and everything else that you get from adding things on this slide to B are sublogics, so they also satisfy it. Okay. Now for connexive logics, these are logics which are required to validate the following theses. The first pair are Aristotle's theses, which I'll write with Airy. These tell you that formulas should not imply or be implied by their negations. And the following pair of Boethius's theses, or Bowie, tell you that if a formula implies something, it shouldn't imply the negation of that something, and vice versa. And connexive logics essentially are systems which satisfy these principles. And it turns out one easy way to satisfy something like these principles is to interpret this implication as a kind of biconditional. And so it's also quite common to require, in addition to validating Aristotle's and Boethius's theses, that you also invalidate the symmetry of the implication, so that it is a implication rather than being a biconditional sort of operator. The motivations for this enterprise are varied. Some of them concern conditionals in natural language. Some of them concern conditionals for other contexts. Some of them, and the one that is to my mind most compelling, also concerns an objection to Tarskian consequence, where we read the arrow as, again, expressing something like entailment, which requires, in virtue of satisfying these theses, something like that formulas should not entail their own negations, and no formula should entail some other formula and that other formula's negation. Of course, there are formulas like this in most logics. In particular, contradictions entail their own negations, and tautologies are entailed by their own negations, at least usually. And so connexive logics reject those principles, and so require us to alter, in a sense, the behavior of contradictions and tautologies, and the behavior of negation as it relates to entailment. By enforcing these claims, as I said, the connexivist seeks to place a further constraint on entailment. Also, like in the relevant logic case, seeking to capture the idea that somehow premises and conclusions of entailments must be connected. And rather than requiring that the entailment claims in question are invalid, we just require the validity of their negations to obtain in the case of Aristotle, or conditionally to obtain in the case of Boethius. Connexive logics, just historically speaking, most of the work that modern connexivists build on was done in the 60s, particularly in work by Richard Angel and Storrs McCall. And in fact, these two, especially Storrs McCall, were working alongside Anderson and Belknap in their school in relevant logics around that same time. And perhaps one of the most noteworthy features of connexive logics, at least these days, is that some of them are the first naturally arising contradictory logics, i.e. logics that have a contradictory set of theorems. For example, if we've got more or less standard or natural principles governing conjunction and negation, we're going to get this sort of validity that I alluded to earlier, that contradictions entail their own negations. But of course, with Aristotle, we get that in addition, the negation of this entailment ought to hold. And we get sets of theorems like these and other contradictory sets of theorems in a wide range of connexive systems. So in a sense, these are, yeah, I mean, not just in a sense. So connexive logics, which do allow you to prove contradictory sets of theorems like these, are among the first logics which allowed you to do that, which is part of their, at least historical and ongoing interest. As we'll see, there are other kinds of contradictions one can prove in some connexive logics, but these systems avoid triviality, even though they have contradictory sets of theorems, by being robustly paraconsistent, which is also a reason to be interested in them if you're interested in paraconsistent logics more generally. Okay, so then, given those two things, the program of connexive relevant logic is basically exactly what it sounds like. What I'm going to do is start from a background of relevant logics of the kind that I discussed a moment ago, and add connexive theses to them and see what happens. I think there's some at least historical motivation for this, given that connexive and relevant logic both developed closely together temporally and spatially. And Richard Sylvan, for instance, or Richard Routley, has in the 80s provided for a, oh, why can't I think of the word now? Categorization of logics, according to which relevant and connexive logics are both subfamilies of the broader family of what he called associative logics, which require there to be some association between premises and conclusions. In fact, as to the historical angle, there's a sizable section of Anderson and Belknap's major work on relevant logics devoted to connexive logic and written by Storrs McCall. And attempts to combine connexive and relevant logics were reported already in the early 80s in the first volume of Relevant Logics and Their Rivals, and later in a paper by Chris Mortensen from 1984. And so essentially what this project is a continuation of that work. There have been a few projects of this kind over the last few years, some of which I'll cite a bit later, and some of which have been written by members of this audience. And I'm going to attempt to contribute to that project. As we'll see, even adding the connexive theses or even just Aristotle to standard relevant logics does result in some badness or at least unsavoriness in the sense that I mentioned. Before I get to that, let me just fix some definitions and notation. So language is, these are propositional languages, just sets of formulas constructed out of atomic formulas and connectives. And in every language I'm going to be interested in, we're going to have at least an arrow, an implication or entailment connective, and a negation, but they may also include others such as the familiar lattice or extensional conjunction and disjunction, or perhaps some more exotic creatures that I'll mention a little later, like intentional conjunction or fusion, and intentional disjunction or fission, which I'll write with a circle and a plus sign, as here. Substitution is just going to be a homomorphism from formulas into formulas. And a logic then is going to be a set of formulas which is closed under substitutions and which at least obeys the modus ponens rule, so that when A are OB and A are both theorems, then B has to be a theorem as well. When I'm talking a bit later about logics that have other primitive rules of proof besides modus ponens, it might make sense to generalize this definition of logic. So we require closure not just under modus ponens, but also under the other rules in question. But at least for the main result I'm going to state about logics understood in this abstract way, modus ponens is all we need. Okay. A logic is going to be contradictory if it has a pair of contradictory theorems, and it'll be trivial if it just is the language. And a fragment of a logic in a smaller language than it normally lives in is going to be all the theorems of that logic in the smaller language, as usual. And when the smaller language has a particular collection of connectives, I'm going to state the fragment of the logic in that language just by subscripting the connectives in question. So axiomatic extensions are just going to be when you have a logic and an axiom, the least logic extending your initial logic that includes the axiom, and by that I mean all substitution instances of the axiom. And matrices, as usual, are going to be algebras along with collections of designated values. The designated values should be non-empty, and we're going to use the operations of the algebra to interpret the connectives of the language. So then when a matrix has the same type as the language in question, so connectives appropriate to, or operations appropriate to interpret the connectives of the language, then I will say a model is going to be that matrix along with an interpretation, which is just going to be a homomorphism assigning to formulas elements of your target matrix, which that homomorphism clause is basically the same as I showed you earlier, that the interpretation ought to respect the connectives and preserve logical structure. Right, so then a model is going to be a model of a set of formulas, just in case every formula in the set gets a designated value on the valuation. Okay, so unsavoriness. There's a very simple recipe for showing that connexive extensions of mainstream relevant logics have some unsavory properties, and the proofs of this slide and the next slide are essentially adapted directly from Relevant Logics and Their Rivals 1, but I'm going to break it into two parts just so they fit. Here's the first. Suppose you've got a logic which has Aristotle's theses and conjunction elimination among its theorems and is closed under modus ponens, the contraposition rule, and the two fixing rules. Then we have as a theorem any negated implication whose consequent is negated. Here's the little proof. The one sort of couple of things to note. One, we do have to use the suffixing rule here on the right branch, which allows you to take formulas that appear in the consequent of the premise and put them in the antecedent of the conclusion, and vice versa. So it lets you swap what position the formulas have. And furthermore, the other thing to note is that the reason this works is because we can appeal to Aristotle's thesis on this penultimate line, to this instance of it, and therefore obtain the result. So the things to note here, we do use everything. We use Aristotle, we use the prefixing and suffixing rules. If we didn't have hypothetical syllogism as a derived rule, so long as we have it as one of our rules, then that works. We use modus ponens, and we do importantly use the rule form of contraposition on the left branch here. So that's part one. Part two, if in addition to the conditions from the previous result, your logic either proves double negation elimination or double negation introduction, then it in fact proves every negated implication formula. Here's the proof for if your logic has double negation introduction, and it just uses the same machinery there. We just plug in the proof from the last slide with not B as a substitution instance in for what was previously B, and then we can just use double negation, eliminate, or introduction and some other stuff to then plug B into the conclusion. So since the mainstream logics, relevant logics down to B, and in fact below, satisfy all these constraints, we have that all of them validate every negated implication. So these are highly contradictory logics, since every provable implication gives rise to a provable contradiction, since every negated implication is also provable. And this raises the question of whether these systems are in fact trivial. The answer, generally no, but sometimes yes. Here's a case where we know it's yes. Chris Mortensen, in his 1984 paper, gave a proof that if we add Aristotle's theses to R, obtaining a system RA, then the result is trivial. And in fact, Mortensen's result follows from a more general fact about R that was proved by Bob Meyer, showing that any contradictory logic extending R is trivial. More recently, Hitoshi Omori, in a forthcoming paper, has shown that the same thing holds for the implication negation, or the intentional fragment of RA, which, in accordance with my convention earlier, I'll write like this. And his proof proceeds by showing this particular lemma here, that in the intentional fragment of RA, any implication entailing its own, any implication between a formula and its negation entails whatever you like. In fact, the first result I'll show is that we can also show that Omori's result follows from a more general fact about the intentional fragment of R, just by generalizing Meyer's result down from full R in the full language down to this fragment. Here's the result. Suppose you've got a logic which extends the intentional fragment of R and is contradictory, then it's trivial. Here's the proof. First, note in the intentional fragment of R, basically by using permutation and the axiom form of contraposition, we can get the following result, that A entails that its negation entails the negated self-implication. But then since A and not A are assumed to both be theorems, we can just apply modus ponens twice and get that in the extending logic L, this negated implication holds. But then let A prime be the substitution instance of A, which has only P as the only atomic subformula. But because this system is a logic enclosed under these such substitutions, we have the negation of such a self-implication provable in L. And furthermore, it's just a general property of R and indeed its fragments that any self-implication is entailed by the conjunction of all of self-implications of the atomic subformulas. And so if we have just one atomic subformula P, then the self-implication of P entails the self-implication of A prime. But then using contraposition and modus ponens, we can infer that in L, we have the negation of P or OP as a theorem. Then if we substitute in for P, this sort of funny looking, quite simple nested implication between Q, then we can prove the negated implication of that. And it's a fact about R that from precisely this kind of negated self-implication, we can infer the negation of the atomic formula in question. But then, since L proves this, and it's an extension of the intentional fragment of R that's closed under modus ponens, we have that not Q is a theorem of L, and so by some substituting, we can get that every formula is a theorem of L. So it's trivial. So that gives us, as a corollary, RA in the intentional fragment is trivial, because using Omori's lemma, we can then find that in addition to satisfying all the constraints of the previous theorems besides being contradictory, we can also show that the system is contradictory by taking this substitution instance of Omori's lemma, and it just contradicts this instance of Aristotle. So the upshot here is, and this will matter for talking about intentional fragments later, the intentional fragment of R and its extensions are bad places to store your connexive theses. So we need to look elsewhere if we're going to try to find interesting connexive relevant logics. But we can do better by going a bit weaker. These are basically the main results of Mortenson's paper from 1984 that I mentioned. And that is that we can add at least some connexive principles, namely Aristotle, to E, and this gives rise to some interesting results. We'll know that in this system, EA, you can prove every negated implication, but nonetheless, EA satisfies the variable sharing criterion, and it satisfies the Ackermann property. These are the two, well, the Ackermann property is sort of one of the distinctive properties of E and its subsystems. And the fact that E satisfies the Ackermann property is one of the reasons Anderson and Belknap gave for preferring E over R. And what this shows is that those properties of E are preserved by adding at least Aristotle's thesis to it. All right, and since both of these properties require certain formulas not to be provable, we know therefore that EA is not trivial. And this speaks, again, as I mentioned earlier, to E's robust paraconsistency. You can even add contradictory theorems to it and it doesn't trivialize. But this also has something to do with the fact that in E, negated implications don't really do a lot. So adding a bunch of negated implications doesn't change much about the logic. There's a very general result in relevant logics in their rivals, volume 1, to the effect that adding a bunch of negated implications to E doesn't really allow you to prove much that's new. Shameless self-promotion. These facts about EA provide us a means to build consistent theories in it, if you understand the word theory in just the right way. And if you're interested in that, you can see a paper that I wrote with Franci Mangraviti in the Journal of Philosophical Logic. Okay, so that's sort of the set of preliminaries and more or less known results. And the question now is, how can we tweak these systems in order to avoid the unsavoriness result? How can we take, for instance, EA or subsystems of it, or subsystems that also include Boethius's theses and retain the nice properties that we want while avoiding unsavoriness? There are 3 avenues. You had a bit of a spoiler if you read my content slide closely, but I'll reiterate them. Basically, the 3 avenues come from the 3 things it makes sense, at least, to reject from the proofs of unsavoriness that I gave you earlier. We can either, in the first place, get rid of contraposition, even in the rule form, and obtain ill contraposing logics. We can drop the extensional connectives, lattice conjunction and lattice disjunction, or we can drop one or both of the fixing rules and have ill fixing logics. And as I said, these basically correspond to the key moves besides Aristotle needed in the proof of the first unsavoriness fact. I should say I split it up into 2 in part to show the role that double negational equivalence is playing in the unsavoriness fact 2. I like double negational equivalence and I don't really want to give it up. But furthermore, as you can hopefully see from those results, it doesn't actually matter too much if you don't have either direction of double negation equivalence, even though you might not be able to prove every negated implication. If you don't also do one of these other things, you're going to still be able to prove every negated implication whose consequent is negated, which strikes me as bad in basically the same way that proving every negated implication is bad. Perhaps as an analogy for why I think it's just as bad. It strikes me that dropping double negation equivalence and then saying it's fine, we can't prove every negated implication, but only the special class of them, is sort of similar to trying to claim that minimal logic is a paraconsistent logic, because you can't really prove explosion. You can only prove that from a contradictory pair of premises, you can infer every negated formula, any negated formula. And that strikes me as missing the point in basically the same way that just dropping double negation equivalence misses the point here. So I'm not going to talk about double negation equivalence. I'm just going to focus on contraposition, intentional fragments, and the fixing rules. Right. The first class are the ill contraposing logics, and these are the logics that reject the rule form of contraposition. So also perforce, given we've got modus ponens, the axiom form. And this is by far the most popular move to make, at least in connexive circles. For instance, this is the approach embodied, especially in recent work by Heinrich Wansing and those in the so-called Bochum school, or following the Bochum plan for negation and connexive logic, where what Wansing does is to reject contraposition, but to then add another equivalence, which is essentially the equivalence version of one of the Boethius principles. Well, pretty close to it, the second one, which tells you that negated implications just are implications to negations. So the Wansing approach involves, in a sense, sort of collapsing the distinction between negating an implication claim and just negating the consequent. And by going this sort of way, by dropping contraposition, maybe building in something like this, you can build in rather a lot of behavior into implication and the lattice connectives. In particular, Wansing's approach has been to start with the positive fragment of intuitionistic logic, and then add a negation which satisfies double negation equivalence, the De Morgan principles, and this sort of thing. And it turns out you can get a nice looking logic this way that doesn't trivialize and also doesn't have this badness fact. So this is one way to go. So what we could do to get a connexive relevant logic is just to start with the positive fragment of some relevant logic rather than that of intuitionistic logic, and build negation in directly, satisfying some of the principles we want, perhaps including something like this, but not necessarily doing so, and thus get some logics. There have been a few recent such approaches, one by Yale, started from the positive fragment of R and added a negation which obeys double negation equivalence and Boethius's theses. And he's able to prove a completeness result with respect to an operational, that is an Urquhart style frame semantics. Recently, Luis Estrada Gonzalez and Claudia Tanas Pimentel started from a non-contraposing variant of a logic near B and discussed some variable sharing like properties that obtain. That's another way to go. Nissim Frances has a similar system to Weiss, but he focuses on a natural deduction presentation. And in 2016, Omori gave a sort of related system again, this time using ternary relation semantics. So by far, the ill contraposing option is the most investigated one. And if you're coming at this question from a connexive background, it's probably the most compelling option. However, I think from the kind of relevantist perspective that I come at the issue with, the rejection of contraposition is a little bit undesirable, especially according to that story, which has it that a central part of the logical behavior of negation is that it induce a downward entailing or an antitone environment. That's just what contraposition says if we understand the order in question here to be that induced by provable implications. The rule form of contraposition just tells you that negation is an order inverting operator, which is to say it's antitone. And this is part and parcel of a story I'm quite enamored with, which is the Gaggle theoretic story of the meaning of logical operators, which takes entailment to be central, and it takes the key behavior that entailment expresses to induce an order on propositions, so that then the behavior of other logical operators, including also the entailment operator, are given in terms of the tonicity that those operators have with respect to that order induced by entailment. This isn't a non-negotiable part of the relevant enterprise, of course. We could absolutely reject that, and some people have. But I think it would be nice, again, coming from this sort of perspective, taking this picture of a theory of meaning for logical connectives, it'd be nice if we could consider logics which preserve at least a rule form of contraposition. So that's what I'm going to focus on for the most part, except to tell you that these other approaches exist. And in the remaining 2 parts, I'm going to focus on logics that have contraposition, either at least in the rule form or in the axiom form. Warning, the results upcoming are sort of partial and a bit patchy, and there's work to be done here. So if you want to think about it or do some of the work, please let me know. I'd be happy to talk about it. Right, so the first option, basically following the move that Omori showed to be shut off, and that follows from this general fact about intentional fragment of R, we could go to intentional fragments. And then that would just involve removing the extensional or the lattice operators, and perhaps in favor of intentional counterparts. In the setting, at least of intentional R, there are nice simple definitions of intentional connectives, or what in the linear logic literature are called multiplicative connectives. We can just define intentional conjunction, intentional disjunction in terms of arrow and negation like that. And that gives us a bunch of nice things. So these operators are commutative and associative, and furthermore, satisfy at least some of the things you want out of a conjunction, or indeed out of a disjunction. In fact, one of the reasons people have been interested in intentional disjunction is that it allows us to preserve or recapture a form of disjunctive syllogism stated in terms of the intentional conjunction and disjunction. But as we've already seen, the intentional fragment of R is a bad setting for connexivity, but the general strategy of trying to start from intentional fragments of relevant logics and build in connexive principles is still a live option, which I'm going to discuss. So right off the bat, there's a very easy argument to show that some intentional fragments work. At least work to get us some of what we want. What I'm going to do is discuss a system I'll call RW minus, which is what we get if we take B and we just add the axiom forms of contraposition, prefixing and suffixing, and permutation. Note, in particular, we don't add the principle telling you that the law of excluded middle holds, what's sometimes called a consequentia mirabilis sort of principle. And what I'll do is discuss a system that has this ugly name, RWAB minus in this fragment, which results from adding to this system Aristotle and Boethius. Sorry, there's actually a typo here. This should be the rule form of contraposition and not the axiom form. So keep that in mind. I mean the rule version. We can show right away that this system doesn't prove every negated implication. In particular, it doesn't prove every negated self-implication, because there's an easy counter model, which is just take a Boolean algebra, add implication defined in terms of material equivalence, and bing, bang, boom. Now, for reasons I mentioned, we don't want this to be the only interpretation, because we don't want implication to be a biconditional-like operator. So in fact, it'd be nice to have to know that there are some other models that allow us to show this, and in fact, there are. But you can see how this model works from this short proof. Yeah, this system RW minus and its extension differs a bit from the usual system called RW in the literature. Noticeably, we reject the principle of excluded middle and this thing. And in fact, I don't know, and I can't find a counter model to any negated implication in the system that we get by extending this logic by this LEM implying principle. So it might be that that's not allowed, even in this intentional setting. Before I strengthen the picture here, I guess I have one more slide where I'm going to talk about fusion. Note, in the case that we have fusion in the language, we've added it not by definition, but as a primary connective obeying this rule, sort of a residuation principle telling you that the arrow residuates this fusion operator. And so we can have an intentional conjunction. It's a bit harder to decide, and there's not a lot of consensus on what a primitive intentional disjunction ought to look like. One obvious thing we could do is add this sort of double direction rule that mimics the behavior of conjunction and disjunction with respect to negation, so that if we look at this as though it's sort of a sequent rule where we combine the premises via fusion and the conclusions via fission, then we can pop things from the left to the right by adding a negation or vice versa. That's one candidate. This basically results in just forcing the definition of fission that I mentioned already in R, which is one way to go, but it runs counter to another way to go, which would be to enforce a version of the De Morgan laws to hold between fusion and fission, which would require then that this should be a fusion, that B fused to C is the same as this thing. There's defined as that, which generally doesn't hold in this setting. So we can add fusion, but when it comes to adding fission, we have a choice between either mimicking this sort of behavior and getting something like disjunctive syllogism out of the mix, or we can enforce the De Morgan laws, and that's basically our choice point. And I don't see strong reasons for going one way or the other, but these are the options. Okay, back to RWAB satisfying the properties we want. Well, I say it's definitely relevant. I'll complicate that in a moment. But we do know at least it's connexive. So it validates Aristotle and Boethius's theses. And in addition, we can give one model which invalidates both some negated implication and the symmetry of the conditional, so long as we then trade out the axiom form of contraposition for the rule form. And I wanted to show you this model because I think it's kind of neat. Take the 6-element matrix that we get from the additive group of the integers, mod 6. That's this guy. And then take its negation, essentially, or take the subtraction in that group as implication, and then define a kind of funky negation out of it. And we can then, in that model, show both that actually negated self-implications are not valid, and furthermore, that the implication is not actually a biconditional operator, which is fun. So RWAB at least satisfies some of what we want. We can add fusion in a way that allows us to avoid the unsavoriness and gives us a genuinely connexive logic in the sense of what we need to validate and what we need to invalidate. Problem. I said on this slide it's definitely relevant. That's a question. And we can see how it's a question by comparing it with a recent system proposed by Amori and Andy Kapsner, which they call AM3, which, as the name suggests, has a 3-valued characteristic matrix semantics. It's tabular. AM3 also extends positive RW, and it includes both the axiom and rule forms of contraposition, as well as Aristotle and Boethius's theses. In addition, it satisfies some of what Andy Kapsner has called strong connexive principles that I'm not discussing here. And it does so by having an intuitionist negation, and so rejecting double negation elimination. But since it's a 3-valued logic, you might expect AM3 to not have the variable sharing property, and in fact it doesn't have it, because you can prove something like this. And RWAB is in a somewhat similar predicament here. Like AM3, it's pretty easy using the last model to see that RWAB will invalidate weakening in this form and in that form, but it's unclear, at least to me, whether it satisfies variable sharing. I have sifted through a bunch of potential models and haven't found any that do the work. And in particular, I haven't been able to find any models of any intentional connexive relevant logic that include both the rule form of contraposition and the fixing rules, which also has the variable sharing property. I haven't been able to find any of the models that you would normally use to show that these logics have the variable sharing property. So as far as I know, as of now, it might well be the case that the co-presence of rule contraposition and Boethius's theses defeats variable sharing in some way, though I don't exactly see how. If you have any insights into this, I'm very curious to hear them. But I'll say that the example of EA that I showed you earlier shows that in general, variable sharing can hold in the presence of Aristotle's theses, but it may not be possible if we have all the connexive principles around, including Boethius. So the results here with respect to intentional logics are, I think, kind of interesting, but a bit equivocal. I'd like to know more about whether variable sharing holds or whether it doesn't. But at very least, we know that there are some systems that are fully connexive, that are not unsavory, and that look, at least at first blush, reasonably natural. So depending on what standard you have for naturality, I suppose. So I think this problem of figuring out variable sharing in this context is basically the main hurdle here to get over for considering intentional fragments as a strategy, allowing us to build in connexive principles while retaining some form of contraposition. Maybe it doesn't work, but I think at least as of now, there's potential. Okay, let me move on to the third option, which are the ill-fixing logics, logics which reject one of the fixing rules. These are these rules, recall. And when we drop one of them, we open up a bunch of options for what kind of axioms and rules we can add while avoiding unsavoriness. We do, however, have to be a bit careful if we try to retain the suffixing rule, the RB prime rule here on the right, as we can sort of dualize the proof I showed you earlier for unsavoriness using just that rule if we do it with disjunction rather than conjunction. I'm not going to talk through this proof at all, but if you look at it, you can at least, I hope, see the same kind of structure going on. We just talk about negated disjunctions rather than negated conjunctions. Right, and then with double negation equivalence, we get from this first phase of unsavoriness to the second phase in the way I showed you before. Okay, so based on that, from what I'll show you over the next few slides, we have rather a lot of leeway with adding prefixing. So we don't have to get rid of all the fixing rules, but we can still have prefixing as long as we're careful in how we do it, but we're much more constrained in adding suffixing. So if we do add suffixing, then we've got to get rid of either lattice disjunction or contraposition or modus ponens or hypothetical syllogism, none of which I want to get rid of. And getting rid of any of them would involve doing one of the previous strategies rather than trying the ill-fixing strategy. So what I'm going to do here is display three ad hoc logics, and these are patently ad hoc and ugly logics that I found with the help of John Slaney's matrix generator for implicational calculi, MAGIC, which allow us to combine connexive principles with other principles so long as we remain ill-fixing in some way, either by dropping both the fixing rules or by dropping suffixing. All right, I warned you, these are deeply ad hoc logics. Here's the first one, thing one. Thing one is what we get if we drop both prefixing and suffixing. Just to walk through a little bit what this logic is, it is like B, an extension of De Morgan lattice logic or first degree entailment. So we've got all the distributive lattice properties. We've got, in virtue of these two axioms here, all the De Morgan laws and the axiom form of contraposition as well as its rule form. And in addition, we can add this principle that has been sometimes called conjunctive syllogism, which is Ross Brady's favorite axiom, which allows us to recapture the behavior of the hypothetical syllogism rule. And in addition, we can add the Lava-Suited middle and the connexive theses. And we can show that in this logic, we avoid unsavoriness by means of this counter model. And in fact, the thing we can show is strictly stronger, that thing one doesn't prove any negated self-implication either, or doesn't in general prove negated self-implications. So if we get rid of both, we can build in some of these things and still get a system. Here's another one. We can retain the rule form of prefixing so long as we drop Boethius's thesis in the basically the same. If we take thing one, drop Boethius's thesis, and add the rule form of prefixing, we can then also get a system which avoids unsavoriness, as can be seen by this counter model. But there are some limitations here. So, and places where some proofs are wanted. I don't know whether you can add fusion to this system without having it become unsavory again. And I don't know whether we can add Boethius's law or Boethius's theses without also getting unsavory. But one thing I will note about this ad hoc system is that this is a proper sublogic of EA. So this is an example of an ill-fixing system, which is at least partially connexive and which also has the variable sharing property. So this is, I think, at least a place to start sniffing around for systems satisfying the properties we want, or that I want. Okay, thing three, this is the last thing. If we get rid of the suffixing rule and trade out the axiom form of contraposition for instead the rule form, then we can take thing two and tweak it so that we have all of our connexive principles. And indeed, in addition to that, we can also add this weak form of contraposition, which you might like for some reason, and also show that that's unsavory, or is not unsavory, by means of this counter model. I should note the counter models I use are generated for thing two and thing three, extend LP by means of some sort of connexive conditionals. So this is a way we can go. Again, adding fusion seems to cause problems. So I'm not sure whether fusion is somehow incompatible. Well, there's a sense in which fusion is incompatible with dropping the fixing rules. But it might be that something like fusion is addable, but I'm not sure. All right. So if we go into ill-fixing land, the ad hoc systems I just showed you, the things, serve basically as proofs of concept. They're not especially natural logics, but I think they point in a direction that we can go for combining connexive theses with relevant logics and getting something savory. So in all of these systems, we get to retain first degree entailment, we get to retain some form of contraposition, and a number of other properties of the connectives, including some transitivity for the arrow, which we lose by, or which we lose in some sense by dropping the fixing rules, in the sense that we at least get to retain this conjunctive syllogism principle and its associated rule. Now, without the fixing rules around, we can't generally extend these systems by something like by fusion, although maybe we can do it by something like fusion. And we won't be able to obtain standard ternary relation semantics, which is a semantics I quite like. But this kind of system is amenable to a different kind of semantic treatment using a generalization of the ternary relation semantic framework that I've recently worked on with Nicholas Ferenz, that was introduced by Peter Lavers, where we take the ternary relation and we neighborhoodize it in the sense of allowing the latter two places of the ternary relation to be occupied by sets of points rather than individual points. And if we use that sort of framework, we can cook up some kind of semantics for these systems. So I guess the takeaway for the ill-fixing thing is that it is in principle possible to go this way. We can get some of the things we want out of relevant logics while still preserving connexive theses. I'm not sure at this point whether either thing one or thing two satisfy variable sharing. I do know that, whether thing one or thing three satisfy variable sharing. I do know that thing two satisfies variable sharing because it's a sublogic of EA. But even so, thing one and thing two still seem to me to sort of point in a direction that we can go for pursuing this ill-fixing strategy. Okay, let me wrap up. Various forms of connexive logics are, as I mentioned, pretty natural contradictory logics, and there are historical and philosophical affinities between connexive and relevant logics, as I discussed. And so it seems to me like connexive extensions of relevant logics are worth investigating. What this talk has tried to do is to point to some problems that we should avoid, some properties we should avoid while building such systems, and has laid out some preliminary results showing avenues we might go down and some open problems to be solved with respect to those avenues. But this is an area where, because it hasn't gotten much attention, there's very little in the way of general results. So there's a lot of, well, there's some work to be done here. And this talk and the paper that it's based on is an attempt to introduce some systematicity into the area and to try to start mapping out the problem space and the space of logics in this area and what needs to be worked on. The major thing, in case, I guess the major takeaway, or the major open problem that needs to be solved here is the question of whether, or to my knowledge, open problem, is the question of whether we can construct these sorts of systems while retaining variable sharing, or if variable sharing has to fail in contexts like these where we have some form of contraposition and the fixing rules and Boethius's thesis. So yeah, those are some things to think about and some sort of strange looking logics for you to chew on. Here are some of the references that I referenced. Thank you for your attention.